Hello everyone, my name is Haghighi. I'm the head of developer ecosystems group in UK and Ireland. So basically we've got a group of developers working with enterprise, academia, startups, and so basically our job is to engage developers and get them excited about IBM products, but at the same time we are trying to be agnostic, so we are not kind of just bound to IBM. So my team, they basically have a very wide range of background in terms of blockchain, Java, cloud, and IoT. So we've got a number of meetups here in the client center happening twice a week. So I really encourage you to attend. I've seen some faces actually who have actually attended our meetup, so that's great. So if you can attend, that would be great. Just keep checking our webpage, and we've got a number of interesting code patterns. They are basically recipes to create different solutions from scratch based on IBM Cloud. And the team here, they're going to be helping you out creating those solutions. So today I'm going to talk about algorithms in Java, and my approach is from the gateway point of view, because in IoT gateways are playing a very important role. Just a little bit about my background. So I was a software developer at Sun Microsystems and an ambassador. Basically, I was evangelizing developers to kind of convert to Java back in 2007, 8, 9, 10. And then right after the acquisition, I kind of carried on working for Oracle for a while. Then I did my PhD with the BAE Systems and University of Bristol, a number of projects as well, and then I moved on to Intel. I was a research scientist at Intel, and a technical lead. We had a very large project in the UK, but mainly we were working in London, with London universities. I'm going to go through that in a little bit. So that's where I worked on gateways, IoT gateways. And now I'm working at IBM. So the first project that I'm going to talk about is the use case of IoT gateways and how you can actually use IoT gateways to do data aggregation and analytics in the field. And for that particular one, I'm going to talk about ICRI, which is an initiative, research initiative in the UK run by, led by Intel and a number of universities. So we chose Queen Elizabeth Olympic Park as our test bed, which I'm going to talk about it in shortly. So then I'll talk about the challenges and solutions for IoT products, and how Java basically came to our rescue. I was a bit biased basically for using Java, but it worked out very well. And then I will talk about algorithms and design patterns for IoT gateways. So, Intel Collaborative Research Institute, ICRI, basically was the main purpose, the goal and the vision for this initiative was to create a fabric for use case inspired solutions in IoT and urban IoT basically. And that's a very important use case in the UK because of the budget and the initiatives and the Horizon 2020 European projects and the number of universities working in that area. So we worked on a number of topics. One was billion device challenge, the other one was citizen engagement, and then creating a sustainable ecosystem. So we chose Queen Elizabeth Olympic Park because it's like a mini city. You've got residential areas, you've got sport venues, a river, a shopping center, you name it. So it was like a mini city within a city. So whatever solutions we created for that park, it was basically applicable to a larger scale for a smart city in general. So for the billion device challenge, we decided to go with a number of devices. The first one was microclimate sensors. Microclimate sensors for monitoring temperature, humidity, air pollution, air pressure, and we've got a large number of sensors across London right now. They have been all deployed. And then the water quality one, which is like pH, oxygen level, ORP, the height of the water. Basically, those are the things that are very quite important for the park owners and the ecologists in the park. And then bats. You might be like, what? Well, bats are actually a very good indicators of the biodiversity of an environment. I had no idea about it. I went to this meeting with my, with the ecologists in the park, and we were just basically, trying to find some excuse for, for putting more sensors in the park. And they were like, "Can you do something about the bats?" And I was like, "Really? Why exactly? Are you trying to get rid of them?" And they were like, "No, bats are like humans. They've got social calls, stress calls, and it's quite amazing. And based on the number of bats and their calls and their species, that they can actually find out whether that environment is healthy enough, or which was quite interesting. So what we did, we created some bat sensors, and they were like just ultrasonic microphones connected to Intel Edisons, picking up the signals and applying a number of algorithms based on the data set, and realizing whether this bat coming from a specific species. And that was about 27 different species in that region. So what we wanted to do, we wanted all these sensors to send data to a number of gateways, and those gateways basically send that to a cloud service. At the time we had Enable IoT, which is Intel cloud platform. That doesn't exist anymore. And then we had this UI, which you could basically see when data comes in. So you could see what the temperature and humidity for each one of those points in the park is. So basically I'm giving all this information for you to understand how Java was basically became quite useful, and the solutions for gateways. So there is another important problem here. Let's say we put hundreds of sensor devices in the park, and some of them are working on using different communication technologies. We wanted to have a solution in place that these sensors are able to switch radio based on the interference or based on the noise level. Because at some point, like during the weekend, for the West Ham United, West Ham Stadium is in the park. So there's a large crowd of people coming into the park with their mobile phones, operating at 2.4 gigahertz under Wi-Fi and Bluetooth. And then suddenly our sensors were like non-responsive. And we wanted to have a way that these sensors become smart enough to switch radio based on the noise level and based on the throughput we expect from them. Let's say for the bat sensors, we were capturing about 1 gigabyte of data per second. That's how much data we were capturing from the environment. But for instance, for the microclimate data, it wasn't that much. So the vision was having an environment with multiple radios operating at the same time, and devices becoming smart enough to switch when needed. So one solution was creating a gateway based on Kora, which is an open source framework based on OSGI that basically goes on a Linux based, usually Yocto Linux, and you could basically just run your application on top of that. So you could have multiple applications running on top of Kora. And Kora is actually quite interesting because it's got this integrated app environment. It's a modular based on OSGI basically. The cloud connectivity side of it is quite easy to define those cloud connectivities. It's got a number of templates. And then the development tools for Kora is actually quite good. There's a large number of development tools, and some of those templates are quite good. So you could basically just pick an application, write your code within that framework, and it's up and running. So Kora basically comes from Eurotech, which is a commercial company, but they basically make that open source. So they've got 2 versions of that, and I'm going to talk about it shortly. But is basically a framework on top of OSGI, and you could have a Linux environment underneath, and then that's it basically. So it's JVM on top of Linux. So any hardware that can have this Linux operating system and JVM, that should be good enough. So what you get out of it is connectivity side of it, network configuration, remote management, and all those things are basically happening in a container on top of JVM. Which makes it quite powerful because it gives you the power to choose the platform based on your need and based on the kind of cost you're looking for. So you don't need to buy it from someone. I'm going to just give you a brief introduction to Kora. So Kora basically provides this OSGI base, but it's important to look at it within the context. It's basically a packaging code, so it can handle events and it can handle codes as a package, and you can deliver it as bundles within the OSGI container. So that's really important because you've got the container and you can basically just inject your application on top of that. The other one is the remote deployment. Once you've got access to Kora, you can just remotely insert your application into the system. Let's say in the park, if you had hundreds of these gateways, you could easily just point them to a GitHub and easily a Git repository, and then easily put that code on, and they all get programmed immediately. That's a very important point. That's the power of OSGI. And then you have MQTT, you could even have CoAP on top of that, so it's not only TCP based, you could have the UDP side of it as well. And once you have that, the power of the combination of MQTT and OSGI is very powerful because it gives you the flexibility, the scalability that you're looking for. And then when it comes to the time synchronization, one of the important points about all these sensors sending data, all their clocks are not synchronized. That's a very important point. For IoT in general, time synchronization is a massive challenge. So Kora has a time service, and that time service allows you to synchronize their clocks before this operation starts, or even during the operation to synchronize their clocks. That's a very, very powerful feature. And the most important one from the IoT point of view, if you're not looking at gateways as data relays, if you've got sensors connected to gateways, they've got this abstraction layer for hardware. So with the abstraction layer, not only can connect any kind of sensors, but also it's about connecting different radios. So if you have a ZigBee radio or 802.15.4 anything, you can easily connect it through SPI, I2C, serial connection, and that's very important. It's just I don't know how many of you have worked with Node-RED, that's just plug and play. Kora is as easy as Node-RED. You can easily just plug and play things together and you've got your system up and running. So, you don't need to buy hardware. I mean, you need to buy hardware, but it's just like a Raspberry Pi. And with the new Raspberry Pis, £5, you can easily have a gateway up and running in your home or your whatever environment you want to kind of capture data from. It's available for BeagleBone based on TI. It's available for Edison, Intel Edison, and it's also available for different commercial M2M gateways. It depends, how you want to create your application, what sort of cost you have for it. But if you go this, the route of open source, you can use whatever platform you want. But if you go on the ESF side, which is the Eurotech implementation of Kora, and they basically maintain that with all the security features and everything, then you have to buy a gateway from Eurotech. So just to give you an overview, this is the commercial stack, and that's the open source stack. It's exactly the same, but it's just you've got the Open JDK on one side, and the other one is Oracle JDK. And obviously, with Yocto, you have a number of security features embedded into Yocto, the one that comes as a commercial stack. On the open source side, you've got to kind of create your own and integrate your own libraries. So going back to the park, so what we did. We thought we just want to have a LoRa network, LPW, low power wide area network. So that's Orbit, looks like Eiffel Tower. We used to call it Eiffel Tower of London. So that's basically the highest point in London, and we managed to get a LoRa gateway on top of that. And even though BT says they've got the highest receiver, IoT receiver in London, that's actually higher than BT Tower. So that's about 115 meter, on top of the park, and it covers the entire park. A single receiver is good enough for capturing data from as many sensors as we want. Let's say 2,000, 3,000 sensors in the park with a single receiver, and that's the power of LoRa. LoRa is based on a spread spectrum, and this technology allows you to capture a very large number of signals, but it comes with a cost, that is the data rate is very low, but you get a very, very large distance. So it's up to 20 kilometers. So you can easily capture data from sensors 20 kilometers away. So I basically installed that gateway myself on top of that. And that was quite interesting because this Orbit, it wasn't actually open. They've got a slide at the moment. And I was actually there before Prince Harry had his first kind of slide coming down from the orbit. Anyways, so then we wanted to create a prototype. So what we did, we created a prototype, and this project is in collaboration with Imperial College, UCL, Intel Labs. I was basically going back and forth between Portland, London, Dublin, and it was like a very, very challenging project in terms of the requirements and the kind of technology we embed into it. So we created a box, and that box basically has, it had 4 different radios, 802.15.4, BLE, Wi-Fi, and BLE, Wi-Fi, 802.15.4, LoRa. So, and then we try to integrate a number of algorithms for this box to become smart, to decide what communication channel you should use, what communication medium you should use for sending that data. And that smaller box is basically just a sensor box with a number of microclimate data. So those are the devices we built. We built about 40 of them, and that's one of them on one of the lampposts in the park. It took us a long time to get permission and all those things to get them up in the park, kind of deploy them. But now, if you go to the Queen Elizabeth Olympic Park, you can easily see some of them on top of that. And that's I basically made them with a group of researchers, and we signed, inside those boxes. Just wanted to, kind of say, yeah, that's our invention. So I'm going to just show you a clip of what actually happened. So this is a simulation and emulation, both of them together at the same time, of the data we captured. So it says it's a very high speed because every signal basically takes about 1 milliseconds to reach the destination, or maximum 15 milliseconds. But we kind of slow it down. Just go back again. And this basically shows about 3 million data points being captured over a day. And that's the stadium in the middle that's round thing. So it's basically all around the stadium, all around the park, all these water quality sensors, air pollution sensors, and microclimate sensors, including the bats. They're all sending data at a very, very low frequency. So it's about every 15 seconds for the microclimate data, and then every 30 seconds for the bats data, and every 45 seconds for the water quality, which you don't even need that, because water quality changes about every 3 or 4 hours. And that's the kind of data we capture. So that's at the end. So why is that important? This is about edge processing. So all these data we capture, we need to kind of process them in the field without sending them to the cloud. Because if we send them to the cloud, then there's going to be a latency between that time we capture data from sensors, send them to the cloud, aggregate them, and then send them back. And that comes at a cost, because if you try to kind of receive data, some results back, that's going to cost a lot of it's going to cost energy, bandwidth, and there's going to be even more noise in the park. So we wanted to have a system in place that we aggregate data in the field, not sending that to the cloud. So for that, you need to have some sort of sorting, aggregation, elimination of duplicate data points, some sort of a storage facility in place, synchronizing all those data, facilities, data storage facilities, and some statistical calculation for, the probability models, how you want to kind of elastically scale in and out the storage, bandwidth, and, whatever applications are running for the concurrency model of that. So what we did, we use game theory, matching theory, utility-based algorithms. I've got a number of publications on that. You can search my name and then find it on Google Scholar. But I'm just going to talk about the implementation side of it. So what we did using game theory basically allows you to make a decision regardless of whatever the others are doing. Matching theory is making a decision based on what others are doing and trying to match that. And utility-based or auction-based algorithms are trying to do that competitively. Let's say if you have like an eBay thing, like an auction. So you try to kind of bid for tasks, bid for functions. So we combined all of them together to define a spreading factor, which is a parameter for LoRa, coding rate, channel, and bandwidth. To do that dynamically using Java. And then once we did that, we could actually optimize latency, throughput, energy consumption, because the nodes are spending less energy if the spreading factor is higher or lower. And then data rate, signal strength, and packet error rate. And those are very important for IoT. So we have all these sensors around, and we don't realize that there is a lot around those sensors operating. With these kind of BLE sensors, you've got a lot of parameters changing at all times inside the chip, and we don't actually realize that until you implement it. So this is just one, the result of some of our research. So for instance, when we set the channel to 5 and then a spreading factor to 7, those are the areas. If you can see on the right side, all of them are actually. So that would be your left. So on the right side, most of the points are receiving a good signal, but on the left side there is not much. So there's like a blind spot basically. For sensor 20 to 30, there's no signal for them, and we wanted to correct that because we didn't want them not to have any signal. And also for the ones who are getting the signal, we didn't want them to have a very low data rate or signal to noise ratio. High signal to noise ratio. So we managed by putting those algorithms, even though we couldn't get them for let's say 26 to 30 because they were like all behind the stadium and they were blocked, but we managed to get the data rate higher, RSSI, receive signal strength higher, and lowering the signal noise ratio. So that's basically what we could optimize using those algorithms. So let's talk about Java. So, as you know, Java Embedded, there's two versions of there are two versions of Java Embedded. One is SE Standard Edition and Macro Edition. When I worked for Sun Microsystems, I used to work worked on the ME Edition. So ME Edition back then it was Sunspots, that's one of them. So back in 2007, there was this sensor network, sensor platform, and that's one of the reasons why Sun Microsystems was way ahead of its time. And this sensor has about 5 different sensors on top, including a battery, including full Java ME stack. So you could just like program your application and just spread them around. So I had like hundreds of them for one of my PhD projects, and they were like scalable, easily programmable, and no problem at all. And Raspberry Pi didn't even exist back then. So Java ME is also available, for instance, for the ARM processor. So K64, so easy. It's about £20. You can buy this and you can run Java ME. That's good enough. That's like Arduino, but you can easily program, run your application, code your application in Java ME, and that's available for free on Oracle website if you want to try it. But on the Java SE side, Raspberry Pi, Intel Edison, BeagleBone, they're all available. So you just put that on and then put Kora on top of that, and you can easily deploy your applications. And I really wanted to, I had no idea that we could do the hands-on, but next time I'll try to kind of start showing you how you can actually run your applications on these devices. So for anomaly detection, that's a very important point, as a complement to Steve's talk. If you're looking for some sort of security issues in the network, you want to look at kind of a large number of, it depends on the sensor network type. But like for most sensor networks, you're looking at multiple data streams, and you want to look at anomalies. This is the data captured over 3 days from 12 sensors. It's the light variation. This is the standardized, data set. That's the same one, but it's a standardized, so you can't actually read it. It's not human readable. So this one, for instance, if you're looking for a single change point detection, as you can see, the system was able to detect that. And this is just Java ME. It's nothing more than that. It's only happening on 100K RAM. So 100 kilobytes of RAM can easily detect that for you on a device which is like less than 25 pounds. If you're looking for multiple change points or anomalies, you can easily see how that could happen. Multiple change points in a recursive manner, that's another one. In a non-recursive manner, all of them have been flagged. And that's the result of creating algorithms and running them in object-oriented environment. So how do you do that? So I want to just very quickly tell you how you can actually create an algorithm. So most of that is based on map-reduce patterns or producer-consumer pattern. Map-reducer pattern, you have to look at multiple streams and then try to kind of find the collections, cluster them based on their common features, and then try to look at them in using multiple threads, and then applying one of these, either greedy, divide or conquer, and dynamic pattern. So if it's greedy, you do it like multiple times in a greedy, let's say, manner. If it's a divide and conquer, you try to kind of break down the solution into multiple problems and then look at each one of them individually. And if it's dynamic pattern, you try to look at them, make some results, make a conclusion out of it, and then go to the next step. So once you have that, you can easily carry on doing some sort of analysis. And by the way, this comes from a data set. Your data set could be a linked list, it could be a queue, it could be any sort of buffering you have. So it doesn't matter. You can easily apply these patterns. These design patterns are applicable to multiple data structures. And then when it comes to sorting and searching, all this data that I've just shown you from multiple sensors, they're just matrices, nothing more than that. You've got a large matrix, it could be 0 and 1s, or it could be the numbers for the RSSI, received signal strength. And then you apply sorting and searching. So you sort them and then search through them to find out what values are the most interesting to you, and then compare them. If it was like game theory, you compare them and make a decision based on what maximizes your own profit. If it's matching theory, you try to maximize or keep your profit compared to the other sensors in the network. And if it's auction-based, you try to competitively try to kind of grab that task instead of someone else, some other nodes in the network. The same goes for binary trees and binary search trees. So you try to kind of create a hierarchical data set and then go through them one by one after each one. So you don't basically look at them all as a set. And in a dynamic pattern, which basically goes with the other one, which was like divide and conquer, you can easily just go step by step, make a conclusion, look at your data set, compare it with the previous results you had, and make a decision based on that, whether you want to go ahead or you want to stop the operation. So that's the way we basically created those algorithms. So some of the design pattern approaches, this is what the kind of data we had from dynamic noise level stabilization. So when we had a very large amount of noise, using these algorithms in the network autonomously, no human intervention, we could actually manage to bring down the noise level that much from that high down to that level, because we switch radio, kind of in a smart manner. And obviously that affected other signals in the region as well. So for instance, when you try to switch radio from Wi-Fi to ZigBee or 802.15.4, then suddenly you are leaving 2.4 gigahertz spectrum. So what would happen is it would affect the BLE, Wi-Fi, and any other devices operating in that frequency. So just to wrap it up, some of the good references for you, I think for this, for the algorithms in Practical Job Algorithms is a very good book, and then the Algorithms in a Nutshell is also very good. So definitely try to have a look at that, look at some of the implementations and the codes there, and hopefully I'll try to in my next talk I'll try to kind of show you some hands-on experience using the sensors and using some networking in the environment to capture data from them. Thank you.